Work, power, energy. Now, you all know that physics is a study of matter and energy and their interactions. The concept of energy is related to the concept of work done by forces. But, however, the concept of, see the difference, okay? The concept of mechanical work is different from the English meaning of the word work. The English meaning of the word work is different and the concept of mechanical work is different. Now let us try to understand the mechanical work concept which is there in our chapter Work, Power, Energy. Here, work is said to be done only when a force or its components causes the displacement in its own direction. Please try to understand. When a force or its components causes displacement in its own direction. What do we mean by this? Let us try to understand this using an example of a block which is kept on the ground, and this block is of mass m, which is kept on the ground. Now, suppose we have applied a force external, let's say of F Newton, which is at an angle of theta to the horizontal. Right? And once you have applied the force F, the body is started moving towards right, and let us say the body has moved by a distance of x. Let's say the body has moved by a distance of x. Say body was here initially, then the body came to this particular position. Let's say it has traveled a distance of x. Now, pay attention. This particular force can be divided into two components. We have already seen that any force which is in a 2D geometric axis y and x can be resolved into two mutually perpendicular components, and the easiest way to give the component is wherever we are moving along the theta, that component is f cos of theta, and its mutually perpendicular component is f sine of theta. Now, the modified diagram for this particular figure is only with f cos theta and f sine theta. Why? Because this f, we have distributed the magnitude of this f in two directions. One is this direction, another is vertical direction. So let me draw a figure again, the modified figure. Now, this mass m is being applied on the right hand side with f cos theta, as the right hand side component is this, vertical component is f sine theta. But we have seen that the block of mass m has been moved by a distance of x, right? It has been moved by a distance of x here. But as you can see that the block has not moved in any displacement or in y-axis direction. So the displacement in y-axis direction is 0. The displacement, let me say the displacement, I can write it as sy, that is the displacement in y direction is 0. So what do you mean by this? So work done is defined as, look at the definition, a force or its components. So what we are going with? We are going with components. Causes. What does this component is causing? A displacement. in its own direction. So F cos theta is causing the displacement in its own direction, which is x-axis direction. And how much is the displacement? The displacement is x. So what is the work done? F cos theta multiplied by x plus. Now vertical component, what is the vertical component? Vertical component is f sin theta. But see the displacement of the body in vertical component, vertical direction. The displacement of the body in the vertical direction is a big zero. So यहाँ पे आ गया f sin theta into 0. So what is the work done? So the work done is, let's say W is f cos theta into x. This is fx cos theta. Right? Now how can we write fx cos theta? We can write the right hand side as two vectors k dot product. So there is one vector which is f bar, there is another vector which is x bar. The dot product between the two vectors is fx cos theta, where f is the magnitude of the force f bar, x is the magnitude of the displacement x bar, and cos is the operator cosine, theta is the angle between the displacement vector and the applied external force. So the work done, the mechanical work done is defined by this particular quantity, f bar dot x bar. So अगर आप ध्यान से देखोगे तो जो डायरेक्शन में फोर्स है वो डायरेक्शन का डिस्प्लेसमेंट को मल्टीप्लाई करना है. नाउ दिस डायरेक्शन फोर्स इज इन दिस डायरेक्शन एट एन एंगल थीटा, राइट? वी हैव डिस्ट्रीब्यूटेड द कंपोनेंट्स, वी हैव फाउंड आउट वी हैव रिजॉल्व द कंपोनेंट्स. वन इज एफ कॉस थीटा, अनदर इज एफ साइन थीटा. नाउ एफ साइन थीटा जो डायरेक्शन में है वो डायरेक्शन में डिस्प्लेसमेंट इज कंप्लीटली जीरो बिकॉज द ब्लॉक इज मूविंग ऑन द राइट हैंड साइड. So the work done in the vertical direction is 0. But what is the work done in the horizontal direction? The work done in the horizontal direction is due to only and only f cos theta. So therefore the work done is only due to f cos theta, and it is f cos theta, that is the entire force in the horizontal direction multiplied by its own displacement, the displacement in its own direction. Now you can relate with the mathematical understanding with the definition of mechanical work. So this is what is the concept of mechanical work, right? Now the units of work is given by, in SI unit it is given by, as you can see, the SI unit of force is Newton and of displacement is meter. So this is given by joules. So the SI unit of the work is in joules. I hope it is clear. So we are done with the work. Let us move on to power. Power. What do you mean by power? Now it is very simple. If we have understood work, then it is just nothing but the rate of doing work. Now I have told you what do you mean by rate. Rate means it is always associated with time. So rate of doing work means at what rate the work is being done. मतलब कितने रेट से काम हो रहा है इसको बोलते हैं पावर. So simple definition is the work done upon time. That means the rate of the work done is power. If W is the work done and T is the time, then W by T is power. Now, we have seen that what is work done? Work done is your F bar dot X bar. This we have seen, right? So therefore, work done W is equal to F bar dot X bar. Now divide it by T, divide this by T. What is on the left hand side? It is power. What is on the right hand side? F bar dot x bar by time t. Now what do you mean by x bar dot time t? This is displacement upon time. It is velocity vector. So the power is also the dot product between two vectors, that is f bar dot v bar. V bar is velocity. So it is a dot product between f bar dot v bar. Thus, power can be defined as the dot product of force and velocity. Now, energy. So we have seen work, we have seen power. Let us move on to energy. Now what do you mean by energy? The capacity of the body, to do work is energy. Means basically what is energy? It is nothing but just the capacity of the body to do the work. Now this capacity, that is nothing but an energy, has following types. It has following types. So this capacity is been divided into type 1, mechanical energy. So what is mechanical energy? All the energy which are composed of kinetic energy and potential energy. Second, we will study these in details, don't worry. Electromagnetic energy. So what comes under electromagnetic energy is all related to electrical plus magnetic and magnetic energy. Third is like light energy. Now this is due to propagation of electromagnetic waves. Fourth comes under heat energy. What is heat energy? Heat energy is nothing but the energy which is transferred or disordered energy between system and surrounding. Disordered energy between system and surrounding. This is a disordered energy. System and surrounding में जो भी transfer होता है, that is comes under heat. Fifth is sound energy. So this is one more type, the sound energy, which is due to vibrational energy of elastic media. Due to vibrational effect of elastic media. Sixth type is biochemical energy. So biochemical energy में आता है all the internal energies due to fissions, fusion. So due to internal energies of atoms and molecules. Right? So these are the six following These are the 6 types of energy, but we shall examine the easiest type of energy, which is kinetic and potential. Right? So kinetic energy is the component of mechanical energy, and potential energy we will also study. Let us study those in detail. So potential energy. So let us study this. Let me say that there is again the ground. We will take the same example, and this ground or earth is referred to as a reference. So this is our reference, and we are standing here, and a ball is thrown up, and the ball is went to an height, let's say h, from this. Right? So always the potential energy is between some reference point. So the reference point is the ball was initially here, it has been thrown up, and the ball has reached to a height h. So since we have taken this as a reference point, the potential at the reference point is, the potential energy here is always 0. And due to this reference, we are measuring the potential energy of any object. So if we are taking this particular reference, we can choose any other reference, right? But generally ground is taken to be a good reference where the potential energy is 0. Now, with respect to this reference, the body has potential energy which is equal to mgh. So this is what is called as potential energy. It occurs due to the position, right? Now, kinetic energy. What do you mean by kinetic energy? Kinetic energy is simple. यही example लेंगे हम लोग. The ball was thrown up, let's say with an initial velocity u, and the person was here, and when the ball was reached to a height h, the velocity was, let's say, v. So what is the kinetic energy at A and B? So this is point A. So at point A, kinetic energy is defined as half m into velocity square, that is u square. And at point B, kinetic energy is defined as half m into velocity square, that is v square. So it is nothing but half mass into velocity square. Now let us see कि ये half m v square ही क्यों आता है. इसका mathematical expression हम लोग देखते हैं. The mathematical expression of kinetic energy. So mathematical expression of kinetic energy. Now kinetic energy of a body is what is the measure of amount of work done by a moving body before coming to rest. Now let us say that a body of mass m is moving with an initial velocity. Let the body of mass m is moving with initial velocity let's say V such that the retarding force F acts upon it and bring it to rest over a distance s. So let us try to understand the mathematical expression. So we know the third equation of kinematics, V square equal to U square plus 2as. Let us apply this. So it is said that it is brought to rest. So rest means final velocity in this motion, that is V, is equal to 0. So therefore this is 0. Initial velocity is, let's say, U square plus 2as. Right? Now here it is moving with initial velocity V, so this will be V square plus 2as equal 0. Right? So this will give you minus V square is equal to 2as. S is equal to minus V square by 2a. This is the S, and from this a is equal to minus V square by 2s. Right? Now we got the acceleration, but what is the acceleration in our case? It is a retarding force. Retarding force means the force which is doing the job of retardation. So therefore negative acceleration will come into picture. That is retardation, which is equal to minus a. What is a? Minus of minus V square upon 2s. You will get V square by 2s. Right? Correct? Now what is retarding force? Retarding force is equal to mass into retardation. That is negative acceleration. So what is this negative acceleration? M into V square by 2s. This is the retarding force. Now work done by this force in stopping the body. The work done by which force? This force in stopping. So what do you mean by work done? Work done मैंने आपको बताया, it is force into displacement. So force is this m v square by 2s into s, which is equal to m v square by 2. See, the equation has been proved. Now this work done in stopping is nothing but the kinetic energy. Hence this kinetic energy, which is nothing but the work done, is half mv square. That's why the equation is half mv square. So this is the mathematical expression of kinetic energy.
On which side of the screen do you think is work being done? Work is being done only on the left side of the screen, where we see that a block is being pushed across the floor. Even though in the second case, the wooden crate is being pushed, there is no work being done. This is because, in physics, work is said to be done only when an applied force succeeds in moving a body. Consider a wooden block which is at rest on a horizontal surface. When the block is pulled by an external horizontal force F, it is put into motion and is displaced through a certain distance d, and we say work is done on the block. Let's consider a second case, where the direction of the force is not along the direction of the motion of the block. Here, the force makes an acute angle theta with the horizontal. In this case, too, we observe that the block moves in the horizontal direction only. Here, the total amount of force is not being utilized to move the block. Only the component of the applied force along the direction of the displacement is responsible for the motion of the block. This component is F cos theta. Thus, here, the work done on the block by the force is the product of F cos theta and displacement. In this expression for the work done, both F and D are vectors, whereas the product, work done, is a scalar. Thus, this quantity F d cos theta is called the scalar product of the two vectors F and D. In vector form, it is denoted by a dot in between the two as shown, and is read as F dot D. Hence, it is also referred to as the dot product. Now let's understand dot product in detail. The dot product of two vectors A and B is equal to the product of the magnitude of the two vectors and cosine of the angle between the two vectors. The result of a dot product is always a scalar. Now, let's see some properties of the dot product of vectors. 1. The dot product of vectors is always a scalar quantity. 2. The dot product is commutative. Consider the two vectors A and B inclined as shown. Theta is the angle between the two vectors. The component of one vector in the direction of the other is called the projection of the vector on the other vector, and is denoted by the product of the magnitude of the vector and the cosine of the angle between them. Hence, we see that B cos theta is the projection of vector B on vector A. So, the dot product of vectors A and B can be written as A into B cos theta, which is equal to AB cos theta. Let this be equation 1. Similarly, we see that A cos theta is the projection of vector A on vector B. So, the dot product of vectors A and B can be written as B into A cos theta, which is equal to AB cos theta. Let this be equation 2. From equations 1 and 2, we see that A dot B is equal to B dot A, which is equal to AB cos theta. Thus, the dot product of two vectors is commutative. The dot product obeys the distributive law. So, A dot B plus C is equal to A dot B plus A dot C. All dot products obey the rule M times A dot N times B is equal to Mn times A dot B, where M and N are just constants. Consider the unit vectors along the Cartesian coordinate axis I, J, and K. The angle between any two vectors in the same direction is 0. Thus, when the two vectors are parallel and in the same direction, then the magnitude of their dot products is maximum. as cos 0 degrees is equal to 1. Thus, we get I dot I equals 1 as shown. Similarly, we get J dot J and K dot K equal to 1 as shown. The angle between any two mutually perpendicular directions, that is, between I and J, or J and K, or K and I, is 90 degrees. And cos 90 degrees is 0. So, I dot J is equal to 0. J dot K is equal to 0. And K dot I is equal to 0. How can we find the dot product of a vector expressed in terms of its components along coordinate axis? If two vectors A and B are expressed in terms of their components along coordinate axis AX, AY, AZ, BX, BY, and BZ respectively, then A dot B is equal to AXI plus AYJ plus AZK dot BXI plus BYJ plus BZK, which is equal to AXI dot BXI plus BYJ plus BZK plus AYJ dot BXI plus BYJ plus BZK plus AZK dot BXI plus BYJ plus BZK equal to AXI dot BXI plus AXI dot BYJ plus AXI dot BZK plus AYJ dot BXI plus AYJ dot BYJ plus AYJ dot BZK plus AZK dot BXI plus AZK dot BYJ plus AZK dot BZK, which is equal to AXBX into I dot I plus AXBY into I dot J plus AXBZ into I dot K plus AYBX into J dot I plus AYBY into J dot J plus AYBZ into J dot K plus AZBX into K dot I plus AZBY into K dot J plus AZBZ into K dot K. Substituting the values of I dot I, J dot J and K dot K as 1 and the values of I dot J, I dot K, J dot I, J dot K, K dot I and K dot J as 0 and simplifying, we get A dot B is equal to AX BX plus AY BY plus AZ BZ. It is also equal to BX AX plus BY AY plus BZ AZ, which is equal to B dot A. As the dot product is commutative, A dot B equals B dot A. Now, using the dot product, we can measure the work done as the dot product of the force and displacement, which is equal to FD cos theta. However, the work done can be positive, negative, or 0 depending on the values of the angle between the force and the displacement theta. The work done by a force is positive when the angle between force and displacement is acute. That is, the angle is less than 90 degrees. An example of this is when an apple falls freely towards the earth. The work done by the gravitational force on the apple is positive. In this case, the angle between the displacement of the apple and the gravitational force is 0. Similarly, when a spring is compressed, the work done by the compressing force is positive. In this case too, the angle between the direction of the applied force and displacement, which is the compression of the spring, is 0. The work done by a force is negative when the angle between force and displacement is obtuse. That is, greater than 90 degrees and less than or equal to 180 degrees. In the case of a rising balloon as shown, the work done by the force of gravity acting on the balloon is negative, since it is opposite to the displacement of the balloon. In the example of a boy lifting a stone, the work done by the gravitational force on the stone is negative, as the displacement is against the gravitational pull. The work done by a force is 0 when the force is perpendicular to the displacement. Consider a block moved over a horizontal surface. In this case, the displacement is along the horizontal, whereas the gravitational force, which is the weight of the block, acts vertically downwards. Here, work done by the gravitational force is 0, since it acts perpendicular to the displacement of the body. As another example, consider a stone tied to a string, whirled in a circular path. Here, a centripetal force acts on the stone to maintain its circular path. Centripetal force is always directed towards the center of the circular path, whereas the displacement of the stone for an infinitesimal time interval is along the tangent to the circle at the point under consideration. As the direction of the force is perpendicular to the displacement, the work done by a centripetal force is 0. The SI unit of work is Joule, which is denoted by the letter J, named after the famous British scientist James Prescott Joule. Thus, 1 joule is defined as the work done on a body when a force of 1 Newton displaces the body in the direction of the force by 1 meter. Now you will learn about the relationship between work done on a body by a net force and the change in its kinetic energy by using the work-energy theorem. According to the work-energy theorem, the work done by a net force on an object is equal to the change in its kinetic energy. We know that the kinetic energy of a body of mass m moving with a velocity v is equal to half mv square. Consider a body of mass m moving with initial velocity u and let the constant net force F act on it. At the end of displacement d, its velocity becomes v. We know from the equations of motion that v square minus u square is equal to 2ad. Multiply both sides with half m and simplifying, we get the expression as shown. We get half mv square minus half mu square is equal to mad. On the left side of the equation, half mv square is the final kinetic energy of the body, and half mu square is the initial kinetic energy. On the right side of the equation, we have the product of m, a, and d. According to Newton's second law of motion, ma is the force on the body. We have on the right side product Fd, which is equal to the work done on the body. This proves that the work done by a constant net force is equal to the change in its kinetic energy. We know that the work done by a force F on a body is W is equal to Fd cos theta, where d is the displacement of the body and theta is the angle between the force and displacement. But in practical situations, a body may be acted upon by a force which may not be constant and is a variable force. A variable force is a force whose magnitude or direction or both vary during the displacement of a body on which it acts. Let's look at an example of a variable force. As the spring oscillates between the extreme positions O and A, the restoring force on it keeps changing with the displacement from the mean position. This is a variable force on the spring.
Work kinetic energy theorem. Now this work kinetic energy theorem is derived from Newton's second law of motion to make the problem solving simpler when the forces are involved on the body. So this theorem is typically effective when our concern is the speeds of different objects in the system at different instants, and when we have no information about the time that elapsed during the process. So what does the work kinetic energy theorem states? It states that the work done by all the forces, work done by all the forces in the system is equal to the change in kinetic energy of the system. The change in kinetic energy of the system. So the work done by all external forces, is equal to change in kinetic energy of the system. So this change can be denoted by delta, that is kinetic energy, that is change in kinetic energy, right? So this is much easier to understand when we will take the problem. So let us try to understand this using a problem, right? Now I will take one illustration problem on how to apply this work kinetic energy theorem. Right. So yeah, let us say there is a block of mass m which is kept on a surface, or you can say which is kept on the ground, and it is frictionless surface. So the ground is frictionless, right? And it is of mass m. Now, let us say the force applied on this mass is in this direction, which is F, and it is making an angle theta, right? So initially the block was moving, let's say, by velocity u, and let's say the final velocity of the block is, let's say, v, right? Let's say it was moving at point, when it was point A, it is u, and the final is, let's say, v, right? Now let us apply the work kinetic energy theorem. Now first of all, क्या दिख रहा है हमको? By all the forces, which all forces are acting? So let me say this block को मैं बाहर निकालूंगा, इसके ऊपर external forces कौन से? एक तो force आपको दिख रहा है, that is F, right? एक force है जो कि हमेशा रहता है due to gravity, that is due to earth, mg. एक force है न्यूटन्स थर्ड लॉ से, मैंने आपको बताया था normal reaction, n. Now this particular force, which is an external force, is at an angle theta. So how many forces are acting on this block? There are three forces. One is normal reaction, another is F at an angle theta, and one is mg. Now ब्लॉक कहां से कहां तक गया? ब्लॉक यहां से लेकर यहां तक गया है. डिस्प्लेसमेंट कितना हुआ उसका? x, लेट अस से, राइट? तो ये जो फोर्स है इसके टू कंपोनेंट्स निकालते. एक कंपोनेंट्स विल बी हॉरिजॉन्टल डायरेक्शन में आ गया आपका f cos थीटा, वर्टिकल डायरेक्शन में आ गया आपका f sin थीटा. अभी इसका काम हो गया बिकॉज वी हैव ऑलरेडी रिजॉल्व द फोर्स f इनटू इट्स टू कंपोनेंट्स. सो दिस फोर्स is gone now. So there are now 1, 2, 3, 4 forces. Now let us apply work kinetic energy theorem. We will just see how to apply. So it is said that work done, this is work done, you can also denote it by W, by all external forces. So let us take one force, one by one एक एक से solve करते हैं. Now normal reaction. Now what is the work done by the normal reaction? Work done में क्या आता है? Normal reaction force into the displacement in its own direction. Now the block is displaced in horizontal direction. The displacement of the block in vertical direction is 0 plus. Now let us take mg. Now mg is also acting downward. The displacement in the downward direction is also 0. So mg into 0 plus f sin theta. F sin theta into displacement is also 0 plus f cos theta. Now see this, f cos theta जो डायरेक्शन में अप्लाई हो रहा है वो डायरेक्शन में डिस्प्लेसमेंट है from point A to B, right, which is x. So it will be f cos theta into x. Now ये जो वर्क डन है जो कि ड्यू टू ऑल द फोर्सेस है, ऑल एक्सटर्नल फोर्सेस बाय ऑल द फोर्सेस इज इक्वल टू चेंज इन काइनेटिक एनर्जी. सो व्हाट इज द फाइनल एनर्जी? हाफ mv स्क्वायर माइनस इनिशियल एनर्जी वाज हाफ mu स्क्वायर. सो इन सच अ वे द वर्क काइनेटिक एनर्जी थ्योरम इज अप्लाइड. So इसमें this term will be 0, this term will be 0, this term will be 0. So you can make use of work kinetic energy theorem where there are multiple forces involved on the body. Yes? Yeah, I hope it is clear. Good.
Consider a body of mass m. The sum of kinetic energy, K, and potential energy, V, possessed by the body is called the total mechanical energy of the body. Let this be equation 1. If a body is displaced due to a conservative force F, which is a function of displacement x, Then, from the work energy theorem, the gain in kinetic energy is related to the work done by such a conservative force F of x and is denoted by the equation delta K is equal to F of x into delta x. Let this be equation 2. Let's now look at the relationship between this conservative force and potential energy. Let delta V be the change in potential energy. As F of x is equal to the negative of delta V by delta x, we get delta V is equal to minus F of x delta x. Let this be equation 3. Equation 3 expresses the relationship between a conservative force F of x and potential energy V of x. We know that mechanical energy is the sum of kinetic energy and potential energy of a system. So, by adding equations 2, delta K is equal to F of x into delta x. And equation 3, delta V is equal to minus F of x delta x. We get delta K plus delta V is equal to F of x delta x minus F of x delta x. Thus, delta K plus delta V is equal to 0. In other words, we can say that delta of K plus V is equal to 0. Let this be equation 4. Since delta of K plus V is the total mechanical energy, we can say from equation 4 that the change in total mechanical energy is 0 for a system all along its path. This is the principle of conservation of mechanical energy, which states that the total mechanical energy of a system is conserved if the forces doing the work on it are conservative. Let's now understand the principle of conservation of mechanical energy. Consider any 2 points A and B in the path of a body falling freely from a certain height h. According to the principle of conservation of mechanical energy, we can say that for points A and B, the total mechanical energy is constant in the path travelled by a body under the action of a conservative force. That is, the total mechanical energy at A is equal to the total mechanical energy at B. Or KEA plus V of x for A is equal to KEB plus V of x for B. Let this be equation 5. From the above discussion, we observe that work done by a conservative force is path independent. It is equal to the difference between the potential energies of the initial and final positions and is completely recoverable. Also, as the work done by a conservative force depends on the initial and final position, we can say that work done by a conservative force in a closed path is 0, as the initial and final positions in a closed path are the same. Let's understand this with an example. Let's throw a body vertically upwards. In this example, we assume that the potential energy is only due to gravitational force, and we take the ground level as the reference level. The body thrown vertically upwards with velocity u has only kinetic energy at A and 0 potential energy at A. Its total mechanical energy is expressed by half mu square. Let this be equation 6. At point B, the body possesses both potential and kinetic energies. The potential energy is mgx and the kinetic energy is half mv1 square, where v1 is the velocity of the body at position B. Total mechanical energy at B is denoted by equation 7. Using the equations of kinematics, we get v1 square minus u square is equal to minus 2gx. Simplifying, we get the expression for v1 as v1 square is equal to u square minus 2gx. Let this be equation 8. Now substitute equation 8 in equation 7. And upon simplifying, we get total mechanical energy at B equal to half m into u square minus 2gx plus mgx, which is equal to half mu square minus half m into 2gx plus mgx, equal to half mu square minus mgx plus mgx. Thus we get the total mechanical energy at B equal to half mu square. Let this be equation 9. When the body reaches point C, that is, the maximum height, it has only potential energy and zero kinetic energy, as the velocity at this point v is 0. Its total mechanical energy at C denoted by mgh. Let this be equation 10. We learnt earlier that the maximum height h reached is denoted by the expression u square by 2g. Let this be equation 11. Substituting equation 11 in equation 10, we get the total mechanical energy at C is equal to mg into u square by 2g. And on simplifying, we get the total mechanical energy at C is equal to half mu square. Let this be equation 12. We see from equation 6, 9 and 12 that the total mechanical energy at all points along the path of the body is the same. Hence, mechanical energy is conserved at all points along the path. Now let's look at another example. The individual on the bike shown revolves in a vertical circle of radius r. The individual along with his bike is considered to be a system. We assume that the potential energy is only due to gravitational force, and we take ground level as the reference level. At its lowest point, which is taken as the reference level, the bike possesses only kinetic energy but no potential energy. Let it be assigned a horizontal velocity u at the lowest point A. At point A, the total mechanical energy of the system is denoted by the expression half mu square. Let this be equation 13. When it is at horizontal position C, its velocity is v1, and the height of C from the reference level is equal to r. When at C, its total mechanical energy is partly kinetic, which is half mv1 square, where v1 is the magnitude of velocity at C, and partly potential, which is mgr. The total mechanical energy at C is denoted by half mv1 square plus mgr. Let this be equation 14. When it reaches the highest point B, it has velocity v, and its height with respect to the reference level is 2r. It has maximum potential energy, which is mg into 2r, and least kinetic energy, which is half mv square. The total mechanical energy at B is denoted by half mv square plus mg into 2r. Let this be equation 15. As the individual moves on the bike, which is together considered a system, in the circular path, a centripetal force Fc, denoted by mv square by r, acts on the system. At position B, weight mg and normal force Fn provide the necessary centripetal force. When the speed at position B is decreased, the centripetal force decreases, and hence the normal force. To complete the motion along the circular path, the speed at B should be minimum such that the normal force on the bike is 0. Thus, mv square by r must be provided by mg, which is denoted by equation 16. Simplifying for v square, we get v square is equal to gr, or v is equal to the square root of gr. Let this be equation 17, which indicates the minimum velocity at B required to complete one revolution of the vertical circular path. According to the principle of conservation of mechanical energy, the total mechanical energy at A is equal to the total mechanical energy at B. Thus, half mv square plus mg into 2r is equal to half mu square. But since v square is equal to gr, substituting the minimum velocity at point B, v is equal to the square root of gr in equation 15. We get half mgr plus mg into 2r is equal to half mu square. On further simplification, we get half mg into r plus 4r is equal to half mu square. Thus, we get u square is equal to 5gr, or u is equal to the square root of 5gr, where u is the projection velocity at A. Let this be equation 18. Thus, from the earlier examples, we see that according to the principle of conservation of mechanical energy, energy can neither be created nor destroyed. It can only be transformed from one state to another. Consider a block attached to a spring placed on a smooth horizontal surface. The other end of the spring is attached to a rigid wall. The position at which the spring is at rest initially is considered to be the mean position, with no displacement of the spring. Then, the spring is compressed and released. You can observe the spring oscillating to and fro from the rest or mean position. The displacement of the block is always measured from the mean or rest position. The spring here is under the action of a variable force, known as the spring force, which always acts towards the mean position or in the opposite direction to the displacement. When the spring is stretched, the displacement is positive. When the spring is compressed, the displacement is negative. The spring force is the restoring force which is responsible for bringing the block attached to the spring back to its mean position. The spring force F is directly proportional to the displacement x from the mean position. Thus, we see that the spring force F is proportional to minus x. We say minus x as the spring force is always directed opposite to the direction of displacement. Or spring force F is equal to minus kx, where k is the spring constant. Let this be equation 1. In equation 1, F is equal to minus kx, which represents the force law for the spring known as Hooke's law. Work done W by the spring force is denoted by the expression integral F dx in the limits 0 to xm, where xm is the maximum displacement of the spring. Let this be equation 2. Since the spring force F is equal to minus kx, we get W is equal to minus integral kx dx in the limits 0 to xm. Let this be equation 3. On integrating equation 3, we get W is equal to minus k into x square by 2 in the limits 0 to xm. Thus, we get the work done by the spring force equal to minus half kxm square. Hence, the work done by the external elongating force will be plus half kxm square. This is the work done by the external elongating force against the spring force, and hence is stored as potential energy in the spring, as given by equation 4. Work done by the spring force can also be calculated by the area covered under the graph of displacement x during elongation or compression taken on the x-axis and the corresponding spring force F taken on the y-axis. The area of the shaded portion indicates the work done by the spring force. In equation 3, W is equal to minus integral kx dx in the limits 0 to xm. We know that the initial displacement is 0 and the final displacement is xm. Instead, if the initial displacement is x1 and the final displacement is x2, then the work done W by the spring force would be equal to the negative of integral kx dx in the limits x1 to x2. Let this be equation 5. Then the work done by the spring force will be equal to half kx1 square minus half kx2 square. Let this be equation 6. Equation 6, where W is equal to half kx1 square minus half kx2 square, indicates the work done by the spring force. Then the work done by the external force W will be equal to half kx2 square minus half kx1 square. Let this be equation 7. Now if the spring is compressed to x2 and brought back to x1, then the work done by the spring force according to equation 7 will be half kx1 square minus half kx1 square, since the final position is the same as the initial position. Then the work done will be equal to 0 as in equation 8. This proves that the spring force is a conservative force since the work done for a closed path or round trip is 0. Thus, we define the potential energy V of x of the spring as 0 when the system of the block and the spring is in equilibrium position. For any extension or compression x of the spring, we have V of x is equal to half kx square. Taking the derivative of the equation of potential energy of the spring, we get minus d by dx V of x is equal to minus d by dx half kx square. On further simplification, we get f of x is equal to minus half k into dx square by dx. Thus, by doing the derivation of the equation of potential energy of a spring, we can easily verify the equation for the spring force as f of x is equal to minus kx as shown. According to the work-energy theorem, the work done by a net force on an object is equal to the change in its kinetic energy. That is, F delta x is equal to delta k, where F is the net force, delta x is the displacement, and delta k is the change in kinetic energy. Let this be equation 9. Now, if the forces acting on the body include both a conservative force Fc and non-conservative force Fnc, then the equation 9 can be written as Fc plus Fnc delta x is equal to delta k. Let this be equation 10. Simplifying, we get Fc delta x plus Fnc delta x is equal to delta k. Since Fc delta x is equal to minus delta v in equation 10, we get minus delta v plus Fnc delta x equal to delta k. Let this be equation 11. We have Fnc delta x equal to delta of k plus v. Let this be equation 12. Since k plus v is the total mechanical energy of the body, which is the sum of the kinetic and potential energy of the body, equation 12 shows that the work done by the non-conservative force is equal to the change in the total mechanical energy of the body. Some forms of energy that we will deal with in this module are heat energy, chemical energy, electrical energy, and nuclear energy. Now, let's understand heat energy first. When satin cloth pieces are rubbed against each other, due to friction, sufficient heat is produced to make the hands feel a rise in temperature. The rise in temperature is due to the rise in internal energy of the body. Here, the satin cloth pieces. Consider that a body is given a push and is then released. When it comes to rest, all its kinetic energy is lost, and a part of this kinetic energy is converted into heat, and the remaining is lost in doing work against the friction. To overcome friction, there is a slight rise in the temperature of the surfaces in contact. Let us look at another form of energy, chemical energy. Chemical energy is produced when the molecules of the reactants participating in a chemical reaction combine to attain greater stability by forming stable compounds. the burning of any form of fuel is a chemical reaction. Burning is an exothermic chemical reaction where the chemical energy of the reactants is mainly converted into heat energy, which can later be manifested in other forms. Thus, in an exothermic reaction, the energy of the reactants is greater than that of the products. Hence, exothermic reactions like combustion of fuels are indispensable in catering to our daily energy needs. There are some other chemical reactions that absorb heat during their reaction and are called endothermic reactions. Some reactions, such as photosynthesis, are endothermic reactions which allow plants to make sugar from carbon dioxide in the presence of air. Chlorophyll acts as a catalyst in the process of photosynthesis. In this case, the energy required for the reaction comes from sunlight. Now, let's understand electrical energy. Electricity is the most convenient form of energy. Electricity is a manifestation of electrical energy and is responsible for running many of the devices in our daily lives, such as electric bulbs, fans, grinders, etc. Till the late 19th century, physicists were of the view that the mass of an isolated system remains constant and it is conserved. They believed that matter can be neither created nor destroyed. It can only change from one form to another. For example, when water is frozen, it turns to ice. The ice melts to water, and when water is heated, it turns to vapor. In all the three forms, the mass of the system remains the same. However, Albert Einstein proposed his famous mass-energy equivalence relation. E is equal to mc square, to show that mass and energy are equivalent. In this relation, E is equal to mc square, and c is the speed of light in vacuum, which is approximately 3 × 10⁸ meters per second. Thus, according to Einstein's mass-energy equivalence relation, mass and energy are equivalent to each other. Mass can be converted into energy and vice versa. When a mass m is destroyed completely, the equivalent energy E is produced. Thus, according to Einstein's mass-energy equivalence equation, 1 kilogram of matter can produce a humongous amount of energy, which is E is equal to 1 × 3 × 10⁸ square joules, equal to 9 × 10⁻16 joules of energy. The energy produced by 1 kilogram of mass is equivalent to the annual electrical energy produced by a power generating station, that is 3000 megawatts. Now, if 1 gram of mass is completely destroyed, the energy produced is expressed as E is equal to mc square. that is, equal to 0.001 into 9 into 10 to the power of 16. That is equal to 9 into 10 to the power of 13 joules. One of the most expensive forms of energy is nuclear energy. Nuclear energy is energy derived from a nuclear reaction, such as nuclear fusion or nuclear fission, from which energy may be released in accordance with Einstein's mass-energy equivalence relation. In nuclear fission, a heavy nucleus like uranium-235 absorbs a slow neutron and hence splits into lighter nuclei. The final mass of products is observed to be less than the total mass of the reactants, and this difference in mass is known as mass defect, denoted by delta M. The mass defect delta M is converted into energy in accordance with E equal to delta M into C square. In a nuclear fusion reaction, lighter nuclei fuse to form a heavier nucleus. This fusion is accompanied by the release of a large amount of inherent energy in accordance with the mass-energy equivalence relation. In nuclear fusion too, there is a mass defect which accounts for the amount of energy released according to E is equal to delta M into C square. The source of the massive amount of energy released by the Sun and the stars is believed to be due to a nuclear fusion reaction, when isotopes of hydrogen, namely deuterium and tritium, undergo fusion to form an isotope of helium and a neutron with the release of a large amount of energy. The energy released is due to the conversion of a mass defect between the reactants and products in the reaction. The law of conservation of energy states that the total energy of an isolated system is always conserved and that energy can only be transformed from one form to another, but can neither be created nor destroyed. For example, when a firecracker explodes, the chemical energy stored in it is converted into light, heat, and sound energy. Nuclear energy is used to produce electrical energy in a nuclear reactor. Different forms of energy are used to do work. Earlier, we learnt that work is said to be done when a force F acting on a body displaces the body through D in the direction of the force. When work is done, energy is transferred. The rate at which work is done or energy is transferred is called power. Thus, power P is equal to work done W by time T. Instantaneous power P is equal to dW by dt. But dW is equal to F dot dr, where dr is the displacement. Therefore, P is equal to F dot dr by dt, which is equal to F dot V, since dr by dt is equal to instantaneous velocity v. Power is a scalar quantity and its SI unit is watt, and its dimensional formula is m power 1, L power 2, T power minus 3. Power can be expressed in horsepower denoted as HP. And 1 horsepower is equal to 746 watts. The commercial unit of electrical energy is kilowatt hour denoted as kWh. 1 kilowatt hour is equal to 1000 watt into 1 hour, and which is equal to 1000 watt into 3600 seconds, and is equal to 36 into 10 to the power 5 joules.